I don't want to announce Soldier of Fortran and talking about some pretty old computing. This is going to blow your mind.
Thank you. All right, so first so while I'm doing this, let's turn that off. We'll start. So while this loads, so that's a common misconception, by the way. So mainframes aren't old, as in like they're not older, it's like a car is old, right? The technology was invented a long time ago. There have been iterations over decades. It's like the fastest processing on the planet. Everything that you own and purchase, a mainframe has touched in some way. Okay, ooh, more people are filtering in, cool. Okay, so before I get started, I have to do this disclaimer. I'm not here in the name of or on behalf of my employer. Everything you see here was done in private time on my own equipment. So they make me put that in there. A little bit about me. So I'm a mainframe hacker. I'm like one of 7 in the world. We all know each other. It's a really tight, small community. When we meet up, like when 3 of us meet up at DEF CON, we have really great turnout because we say it's like 50% of the world's mainframe hackers showed up to the mainframe hacker con at DEF CON. So, you know, it's a pretty cool thing. I created a game in HyperCard called the Mainframe Hacker Choose Your Own Adventure. So you can go and play it. It's on the archive. You can go play this. It sort of teaches you about what's available when it comes to mainframe hacking. I've also spoken a bunch about mainframe hacking. So I got into this because no one was talking about it, and it's a systemically important platform for the entire planet. And so I started talking about this. This is my second time at Shmoocon. In fact, one of my first talks in 2013 was at Shmoocon. So there's a nice little return to giving another talk. I've spoken at RSA, DEF CON, all over the place about this platform. I also create and enhance tools. I don't think there's much point for me just to get up here and say how awesome I am at hacking mainframes if I don't give back, right? So I've created a Lua TN3270 emulator for Nmap. And so what that does is that allows you to interact with a mainframe to do things like VTAM enumeration, kicks TSO user brute forcing, kicks transaction enumeration. Does anybody know what any of that means? Yes. Right? One person. So if you know what any of those things mean, Kix is probably the most important technology on the planet today. If we lost Twitter, people would be upset for a couple of days and just go to MySpace 2, right? If we lost Kix, like there was like a thing that wiped out Kix, it would be global catastrophe. Flights wouldn't go, trains wouldn't move, Walmart wouldn't have stock on shelves, okay? So I write tools to help pen test those things. I also have created other tools like a Rex enumerator. So there's Jim Taylor and Ayub Al-Assal, that's the 2 of the 7. They've helped create these scripts where we can do user system enumeration. So who here has their OSCP? No one? Wow. So if you're doing your OSCP, the important thing is enumeration, right? Once you get on a box, you enumerate and enumerate and enumerate to find more things to do privilege escalation. Nothing like that exists on the mainframe in terms of tools, right? There's no Linux priv checker, there's nothing, right? So we have to develop the tools from scratch to do those kind of things. I also run the IMP, or the Internet Mainframes project. Why are you clapping? It takes screenshots of mainframes on the internet. No claps. So what the IMP does, if you go to that website on Tumblr, if you go to mainframesproject.tumblr.com, you will see things like this. This is an internet-facing mainframe. So what the tool does, it's like basically Nmap and Bash and Python and some other stuff all glued together to, so I don't want to talk about Shodan, but Shodan lightly supports TN3270. But this will go and take a screenshot automatically and paste it to Tumblr with the IP address and the port, right? So if you wanted to see this yourself, no, I don't do this because I'm not trying to name and shame. I'm doing this to raise awareness that these are there. These to me are no different than the AT&T employee logon page, right? It's just a logon page. It's not any different just because it's a mainframe. I also teach a class called the Evil Mainframe Hacking class. I teach that with Chad Rickensrud or Big Enny and Smalls. And so together we teach this 2-day mainframe hacking class where we know this because we've asked. It's the only class on the planet that has a mainframe CTF. It's the only place you can go to get a mainframe CTF because no one else offers it. We've asked people to do that and they wouldn't. Now, if you were coming to this talk hoping to hear about AS400, you're going to be very disappointed because I'm not talking about AS400 at all in this talk. This talk is just about ZOS, but it's really about ZOS privilege escalation. I'm not going to spend much time on sort of the basics. I've talked about that enough. If you go on YouTube, you can watch 10 hours of me talking about VTAM, TSO, kicks, network job entry, JCL, all this, Rex. You can go watch those talks. I don't want to talk about that again. The most important thing to know about the platform for this talk is it runs Unix. Just regular Unix. Who here has ever used AIX? Okay. Very similar. It's very similar. So we have Unix that runs on the mainframe. It's not, okay, how do I put this? It's not running on the mainframe. It's part of the ZOS operating system. But it's not, almost like a container, okay? But it's an important container because it drives all TCP/IP. But it's regular old Unix. You have files, folders, all kinds of stuff. And it looks like this. Here we go. Just regular old Unix. Right? Everyone who's afraid of mainframes and, oh, it's just Unix. In fact, we call this the gateway to mainframe hacking because it's easy for people who don't know mainframes to come in and mess around in the Unix side before they graduate into the more harder TSO stuff. So look, it's just Unix, just regular Unix. Now, when we talk about mainframes, there's an important concept called the authorized program facility. What that means is basically you have a folder, or you have lots of folders, and any file that you put, any executable you put in that folder. Now, if there's mainframers on the stream, don't give me crap. I'm just dumbing it down, all right? So you have folders, because they're technically called partition data sets, and libraries. You have folders. In that folder, you put an executable. When you run that executable, it is allowed to run as authorized. But what is it authorized to do? Does anyone know? I mean, yeah, run, but anyone know what it's authorized to do? Man, this is going to be a rough morning. Whew. Everyone had a good time at the party, huh? So, there's a bunch of stuff it can do. Basically, if you can run an authorized program, you can take over the operating system. You can change any region of memory, including protected regions of memory. So if a region of memory is protected, you can't change it unless you're authorized. So if you get APF authorized, you can change any region of memory. This gets important in a couple of slides from now. You'll see why. So just know you have an APF authorized program. When it runs, it can change any location of memory. That's the most important thing to remember. Now, security on the mainframe is kind of weird. They have 3 products. They have RACF, Top Secret, and ACF2. RACF is the market leader. It's like 75% of the overall market is RACF. So RACF, so think about you're designing a security system in the 70s and 80s. And you have a database. It's a monolithic database. Every single access permission is in one database. All your users log in Monday morning, and they go to access a file. And your hard drives are very slow. It's going to take forever, right? So to save on time, what happens when you log on to the mainframe is ZOS takes a portion of your record in RACF, like your access rights, and puts that in memory. So when you're doing something on the mainframe, it goes into memory and checks your access rights, which is fast to access, instead of having to go to disk all the time. So you log in, it copies that location, you go access a file, it looks in memory to see if you're allowed to access that file. We following along? Okay? That data structure in memory is called the ACEE. This is a heavy talk for 10 a.m. after the party, huh? So, I'm telling you, it's going to get worse, so buckle up. So, at offset 26, or 38 bytes in, on the ACEE is a very important byte called the ACEE flag 1. Anybody want to know? Does anyone in the room know what that flag controls? Someone should have seen my previous talk, I'm just saying. So, if you look at what's in this flag, there are 8 bits. Each bit controls a very important part of what you're doing on the operating system. This is in memory, by the way. Right? So this is, when you log in, it'll copy that flag and put it in memory. If I am system special, that is, if I change the bit, the first bit, to a 1, I can make any change in the RACF database I want. And remember, the RACF database controls all access rights for the entire operating system. So if I can change 1 bit, I can make any change I want to my access rights. If I can change the other bit, operations. Operations is full access to every single file on the operating system, bar none. In fact, if you look at the access tree, like the decision tree for getting access, like the second check is operations, and it stops checking the rest. So it bypasses everything else. That's in memory. So if I can change this byte, I can own the system, right? Okay, the last thing to know. So we've got Unix. It runs Unix. It's got APF authorized libraries. It's got RACF security, which has access rights in memory. In Unix, they added an extra attribute. So instead of just having, read, write, execute, and set UID and stuff like that, there's another extra attribute, ALPS. Don't worry about the L and the P and the S. Don't worry about that. We just care about the A, because this is directly from IBM's documentation. If you set the +A attribute to a Unix file, doesn't matter where it is in Unix, it runs APF authorized. So what does that mean? So let's take everything we just learned, we'll put it all together. So what does that mean? If we can control the execution path of an APF authorized program in Unix, we can own the system. Right? Does that make sense? Following along? Yeah, I see like 6 people. Okay, good. Now, who here has heard of the logic of breach? 2 people? Good. Nice, good. That's better than other questions. So, 2012. A bunch of hackers break into Swedish government mainframes. They steal a lot of stuff. They take copies of their tax database, the tax source code. They run rampant through the system. They get caught eventually. But what's important is that I was originally under investigation for the breach, because in 2013, 2012, guess who was the only public mainframe security researcher on the planet mailing mailing lists? I wasn't even giving talks yet. I was just mailing lists, like emails. And they're like, must be that guy, right? Because yeah, I'm dumb enough to break into a government mainframe and then email about it on the John the Ripper mailing list. So I'm under investigation. But turns out I didn't do it. Otherwise I wouldn't be here. But it was a very, very important figure in the pirating community who was convicted for this crime. I'm not going to name names, but long story short, because of this person, the government was worried that they were going to get blamed for arresting them for piracy. And they wanted to make it 100% clear it was not because of piracy. It was because they completely ran roughshod over a bunch of mainframes. Okay? So they want to make that clear. And how they make that clear? They released every single investigation file that they had, the entire file, 800 pages worth of investigation and analysis and all that stuff. Part of the report's in English, part of the report's in Swedish. I got real friendly with Google Translate. Now, what's really cool is in the report are code snippets of code that works. So because this is a historical event, I took all the code, put it into GitHub. So if you go to that GitHub, the mainframe/logica, all the code that you can find in that report has been copied there. But what's even better is some of the code was obfuscated. Okay, so this is Rex. This is one of the 0 days that the person found. This is the entirety of the rec script. This is all you need to get UID 0 in Unix on ZOS like 110. Okay? This is it. Now, what's important to know is the top half of this script was in the English file, and the bottom half of this script was in the Swedish file. And I gave a talk in Sweden, and they both pointed at each other and said, I thought we agreed on the top or the bottom, right? So, and the other thing is, when they put these scripts in, they were completely broken on purpose. And huge shout out to Oliver Lavery, who figured out how to sort of fix it and get it working, and we worked together to sort of like making this work. So, when you run this, it does that, right? So, you run it, and it gives you a UID of 0. Now, a UID of 0 in Unix on a mainframe doesn't get you much. I think it's more akin to like getting local admin on a workstation in an Active Directory domain, okay? You've compromised a part of the system, but you haven't compromised the whole of the system. You could use this to try to, and there's ways that we know of how to do that, but typically this just gives you the ability to own the Unix side, which most places, that's not a really big deal. Like Kix. Remember I was ragging on Kix? Kix doesn't run in Unix. So if you compromise Unix, you have not compromised Kix. Okay, so all this is happening, right? My name's in the investigation paperwork. I'm like reading code. In fact, it was 2013. I was on my way home from ThoughtCon, and someone emails me, and they're like, hey, why is your name in this documentation? That's how I found out, by the way, was I was reading the report that they had publicly published and saw my email address in there to the FBI. They're like, hey, could you put a hold on this account? Don't let them delete emails. So, real quick aside, did you know that they can just tell Google to hold your emails and tell us where the person logged in from? And they have to do it, unless it's an email account that's only been logged in from another country. So what happened is they emailed Google, and Google was like, we're not doing that because this person's only ever used this account from an American IP address. And then in the bottom of the email they say, here's the person to contact who can do that for you from the State Department if you want to extradite him. So that's cool. So anyways, so this is all happening, and I got a random DM from a complete random, like, no followers Twitter account, right? I'm like, hey, do you know if this pastebin link, and that works, by the way, if you go there, it's still there. Does this work? Is it a real exploit? And if so, is it a known one? Now, we're all cybersecurity experts in the room. What do you think I did when I got this DM? Do you think I instantly clicked on the link like an idiot? Because that's what I did. And this is what came up. Right? This is what we're gonna spend the next 30 minutes talking about. This is DeFeNeStRaTe.C. Okay? This was not part of the investigation paperwork. And it's mind-blowing what it does. So we're going to spend a few minutes. I'm going to leave this up. I'm going to get a quick glass of water here. Any questions so far? What's that? Just to be awesome. I read the code of conduct. Ooh. Okay, also, by the way, we have a prize coming up. And if you can answer a quick question about some opcode, I got a bag of moose droppings to give out. My suspicion is no one's going to be able to answer it, so I'm going to eat this on the flight home. If you're wondering what OMVS is, so there's a little bit here, OMVS. If you're wondering what that is Open MVS, and that's what mainframers call Unix. Because they can't call anything by its name, that would be too easy, okay? And notice the program down here that they're targeting, IOELMD10, okay? That's the only two most important things to get out of this. Now, from a very, very high level, what this program does is it creates a bunch of machine code, executes bpx1exe shellcode, fills an environment variable with the machine code and shellcode, calls this vulnerable program, IOELMD10, and then gives whatever user a shell with ACE priv and ACE racf. Does anybody remember what those two things were? In the ACE flag 1, does anybody remember what those were for? One gives you privileged access. So now in Unix, it's not going to ask for access rights when you're accessing a file. And the other one turns off logging of your activities in Unix. So if you can change those 2 bits in Unix, you can do whatever you want and not have to worry about like logging and all that stuff. Now, as we go through the code, just note I have cut out a bunch of code. In fact, I rewrote it and called it TinyD.C because it's way easier to follow if you cut out all the stuff that's not being used and so on and so forth. So if you ever want to try this, if you have a mainframe at home or you got a mainframe at work and you want to test this out, just use TinyD.C. It has instructions on how to compile it and how to run it. It's even got a vulnerable test program that you can use to run the code if you want to really dig into this. Okay, so the program is recursive, and it'll be obvious later on why it's recursive, but just know for the first time, if an environment variable is passed and payload equals 23 is in the environment variable, it does something else. But on the first run, when you call it, it doesn't have that set. So it's going to call itself on its first run through, right? And on a first run through, there's a bunch of stuff we don't care about. And I'll skip over it, and we'll see why it's important in a bit. Okay, so on the first run through, the very first thing it does is put payload equals 23 in the environment variable. I don't know why. I don't know if this is the 23rd iteration of this payload. Maybe there's 1 through 22 that didn't work. I don't know. But that's what it does. And then it takes this variable called shellcode underscore full and shoves that into the environment variable. Now this is really cool. Shellcode underscore full is actually Z architecture machine code. But it's written in readable C. And I'm not being sarcastic when I say it's easy to read, right? That's not me being like, ha, easy to read. It's super easy to understand. So so first we define a bunch of registers, right? There's 16 general purpose registers. And then down here, which is the important bit, we define, let's see, 1, 2, 3, 4, 5, 6. We define 6 opcodes. Just 6, that's all we need. We just need 6. If you want to know more about what these opcodes do, anybody do assembler programming? Yeah, so these opcodes, very similar, right? There's very similar mnemonics, very similar programming. So you're defining these opcodes, and all of this documentation, by the way, is available freely from IBM in the principles of operation. If you can go read this PDF file, it's got every single opcode, what it does, how it works, what it's shifting, all of it written in English, and you can understand what it's doing. So that's what they've used. They just developed C code to create machine code. Okay, so first we define a bunch of machine language, and then we create the machine code. So this, like, array now is going to be an array of like 56 bytes of machine code. But instead of typing it out by hand, our hacker wrote this code so that it's easy to change, easy to understand. I'll step through exactly what all the code does later. Don't try to understand what it's doing yet, because you can't. But don't worry. All right, so far all we've done is we've created a payload equals 23 and some machine code. Now we need something called shellcode bpx1exe parameters. So we have an environment, we have some variable, some data structure, and then we have a function that fills in that data structure. That's what this data structure looks like. On our first run, none of this matters. This whole part here, none of that matters at all. It can be zeros. In fact, if you look at TinyD.C, what it does is it sets all those pointers to C1. So it's pointing to a place in memory located at C1, which doesn't exist, right? That's for debugging if you want to really debug the program. And then down here we have this, whatever this is, right? Whatever the hell this does, we have all these things down here. Now we have a function. We have a function that builds out and fills in this data structure. And on the first run, none of this really matters. right? So the really only important bit the first time we run through the program is this part here. This is the most important part. And in fact, it's even less than that. It's just this. This is what's important. If you run through the code, this is what's important. We're passing it a length of 7, because that's how long /bin/sh is. That's it. And then we have pointers pointing back to that. You'll see why in a bit. Any questions so far? I feel like this is a pretty heavy talk for a night of partying, so everyone's following along. I just want to make sure, because it's just going to continue to get worse. All right, so. Yeah, oh boy. So what is BPX1EXC? Anybody want to guess? Like, I've given a bunch of clues already. Yes, okay, so BPX is actually the IBM nomenclature for a Unix software. That's their product code. So BPX means it's a Unix thing. 1EXC means that it's an executable and it's a callable service. Okay, so BPX1EXC is a callable service on ZOS that you can use to run programs in Unix. So if you're writing software in assembler and you need to call or run a shell, you use BPX1EXC. There's a whole bunch of these. In fact, Chad Rickenstrud gave a talk at DEF CON that I implore you to check out about writing a buffer overflow, and he used this. In fact, if you look on Metasploit, there are modules in Metasploit to generate shellcode for this platform using JCL and assembler, and it uses one of these things. So if you want to learn more about that, that's the place to go, is look in the Metasploit code. So BPX1EXC expects this data structure. This all should look familiar. We saw it previously when we were talking about our data structures. The path length and path name is just what we're telling the callable service to execute. It's literally that easy. The argument length and the environment length, so there's two separate variables there, is how many pointers to arguments or environment variables should BPX1EXC expect. So you have a list of pointers somewhere in memory. How many of those pointers are there, right? Then you have the length list and the argument list. So that's somewhere in memory. You have a list of all your arguments and how long each argument is. And then same thing with environment variables. So you have somewhere in memory a list of environment variables and how long they are. Okay, that's what BPX1EXC expects when you run it. If that doesn't exist, the program crashes. It does not end well. Okay, so we've built that data structure out. We're good. We're going to continue to fill up the environment variable with something. We're going to fill it up to 4,096 bytes, a full page of memory, and we're going to fill it with this. Anybody know what this does? This is now, who wants a bag of poop? I got a big old bag of moose droppings. It's actually dark chocolate almonds. So I will definitely eat this on the flight if no one gets this right. So okay, so I'll give a hint. It has nothing to do with ZOS at all. So I gave this a similar talk at Sky Talks, and people in the audience knew the answer instantly. No pressure. So close. So this puzzle took me 3 weeks to figure out. It was like the last thing to solve. Not continuous 3 weeks. It was just like every once in a while I'd be like, I still don't know what this does. That's exactly what it is. Who said that? Yes. Come see me, I'll give you this bag. So, can you explain what it does? Do you want to explain? So, this is the foof bug. I like that name. I didn't know it was called that. So, this is an Intel problem with chips. On Intel, if you pass it, the older Intel, if you pass it this instruction, it'll cause the CPU to lock. And so you can't use the computer anymore, right? Big problem. Why would our hacker put that in there? Because they could have put anything. They could have put dead beef. They could have put all F. Whatever, it doesn't matter. They're just filling up a variable with stuff. This thing took me so long to solve, and it's literally just an inside joke. All right, Alrighty. So come up after to get your chocolate almonds. Okay, so we're done now. We're done building our data structures. Now we're going to call ourselves. We're going to call ourselves. See here, this little piece of code here says, if payload's not in the environment variable, we're going to call ourselves. And we're going to build another bpx1exe data structure, but this time to call ourselves. And then we pass it payload 23 plus the shellcode plus the foof bug all the way 4,000 bytes. Anybody know why we're doing it this way? Why are we calling ourselves? Because we don't know where in memory the environment variable will be when we first run the program, so we can't really build it out. But once we call ourselves again, we know where everything is. So now everything's going to be almost exactly the same. Everything's going to be the same. We're not going to we're not going to do the payload stuff. I mean, we could. And in fact, in the original program, it resets the payload stuff and all that stuff, because it doesn't matter. And now we have, though, at our fingertips is an environment variable that we now know the location of in memory, right? So now we have this data structure that's got payload 23, 56 bytes of machine code, 55 bytes that mean nothing. Remember those void pointers? Those pointers that were the C1s? So that's 55 bytes. We have that available to us now to use, and then we have a bpx1exe structure after that. So this is what the first 66 bytes look like. So payload equals 23, and then a whole bunch of machine code. After that, we have our C1s, right? Our 55 C1s. That's what all these pointers are, right? They're blank right now. We will fill them in a second. And then we have our bpx1exe structure. For those following along, so there's the 7, right? Remember we set the path length to 7. And /bin/sh. For those who don't read EBCDIC, this is an EBCDIC. This is not ASCII. Don't ask, but just know that it's an EBCDIC. Now, we need to replace all those C1s. So now that code that was in that function, the build shellcode function, now we can use this part of that code to generate the pointers that we need for the bpx1exe data structure, right? So now we fill all these in, and we're done. We've got this data structure now that we can pass. So we fill up an argument that's another page size of memory called overlay register 14. Anybody know why? When we looked at like the registers, did you see like an instruction pointer? Anything like that? So register 14 is how high-level assembler programs use, that's the register that they use for the return, right? So wherever you're returning to, that's where that's going to get stored. So we're trying to overwrite that with the location of our shellcode. That's what we're trying to do. So that's what this is doing here. So it's going to build up an argument. We're going to pass it to a vulnerable program, hopefully overwrite whatever's in our register 14, and that'll return us to the beginning of our shellcode. That's what we're going to try to do. Now we're going to run our vulnerable program with all this data. We're following along? We're good? Good. All right. So here's what our victim sees. 246 bytes of shellcode plus foof C7, C8, and then an argument that's 4,000 bytes long that contains the pointer to the location in memory of our shellcode. Let's look at that shellcode for a second. So there's two parts. It's easier to think of it when there's two parts. So part 1 and a part 2. Any questions about what it does? No, okay. So part 1, part 2. Is that clearer? Yeah, you got it now? Good. Yeah, did you take a picture? You're going to... Right, so step 1, we're going to get priv. We're going to change that location in memory. So now all the way back to the beginning of the talk. We have an APF authorized program, right? IOE, whatever, LMD, is an APF authorized program in Unix. So when we execute, if we control the execution flow, and we run this, what this is doing is so the first part at the top here, this is putting you into supervisor state, well, putting you into problem mode. What that means is you can edit any region in memory now. So those 3 lines that means, let's see, how many bytes is that? It's not even, let's see, just a handful of bytes here. That sets you into supervisor state. So now you can make changes to memory, whatever you want to do, or sorry, problem state. So what the other part does down here is this is finding the location in memory of your ACEE. Remember I said the ACE flag 1 was at offset 38, like hex 26. That's what this is doing. It's storing one character, 1 byte, and it's overwriting that location in memory. So once this runs, we now are privileged and unlogged in Unix. And then we launch a shell. So we switch back into a different state, and then we find the location. So we're just looking to find the location of the callable service. We're just mapping memory again. And then we branch and save register, BASR. We branch into, we call that executable, and we pass it our list of variables. And this is the part that drove me the maddest, because I had no idea how it was doing it. So there's some magic here, and I have to call it out because it's amazing. So notice BPX1EXE expects register 1 to contain a pointer to the data structure that we set up that launches like whatever executable we want to execute. That's what, so it has to be in register 1. Can't be in any other register. But if you notice, we don't set register 1 to a location in memory at all. And that's because of the genius of whoever wrote this using branch and save. Branch and save, so this is what it specs, right? This is our data structure. Branch and save register will take whatever the following byte is in memory from your code and save that in register 1. And then it branches into register 15. And what's in register, now what is in memory at the next byte location is our data structure. So it calls it, the data structure is sitting in register 1, and we're ready to go. Isn't that cool? I thought that was super cool when I figured that out. It's amazing because it's cutting down on how much, like you're shortening up how much shellcode you would need instead of having to figure out where in memory it is. You know it's the next byte down, so we'll just use this branch instead of a different jump or branch. Okay, and this is what it looks like. This is what that data structure looks like in memory. So here, for those of you who can't read machine codes, all this is the machine code right here, right? And this is branch and save. So 0D is branch and save, BASR. We branch into, we store the next byte down in memory, which is this, that location. We save that into register 1, and then we branch into BPX1EXE. And what is BPX1EXE looking for? It sees this massive data structure here. So let's scroll down a little. So we have this big old data. So first it expects all these pointers. So all these pointers are locations in memory. So I'll explain what this is showing. What's in memory? So this is what's in memory up here. And this is the actual location in memory you can find that, right? When I was doing the testing. It would be different if you ran the program yourself. But now, we have this data structure here. Now if you look, command length points down here. So 1E, whatever, 72. Well, here's that location in memory, which is 7. And then remember what /bin/sh was in EBCDIC? It was this, right? And what is that location in memory? 76, right? So these are all pointers pointing to locations in memory, and goes down. Now what's cool, you go down here, this is an argument. There's one argument being passed, and where can we find that argument? Up here. So it's when you execute this code, it's actually executing /bin/sh, and then that would run. So if you just called it like that, that would just run in the background, because this is a background process. So what you have to do is you're passing one argument to/bin/sh of itself. So you're running bin/sh twice, right? Otherwise, you wouldn't get an interactive shell. So that's what these pointers down here mean. And then look, if you look at the rest of it, it's all zeros and stuff. Don't worry about this. And then that's the end. And then so I put other stuff. Ooh, that's not. So I put other stuff down here because I was like, I don't like the foof bug thing. So I wanted to make sure I understood it properly. So, all right, let's see this sucker in action. So here we have regular old Unix. I'm going to list out the extra attributes. We have a program here called IOE MLD test that you can see up here, right here, is APF authorized. So we have an APF authorized program ready to go. Now look, I'm trying to cat this file. Can't cat the file. I'm trying to do a command that's going to give me system special. I can't run that command. I'm not authorized to run that command. So we'll let the code run here. So notice my prompt didn't change. I'm not root. My user ID is still the same. But because I changed those 2 bits in memory, I now have full control of the operating system. I have essentially at this point a kernel level shell in the system. Isn't that cool? All right. So does it work? Against my test program. No, don't clap. I didn't write this. No, don't. No, it's not like if you want to clap for the anonymous hacker, go for it. But I mean, yeah, actually, yeah, fair enough. Yeah, clap for the anonymous hacker. They'll see the video. Yes, thank you, Anon. So, does this work? Yeah, it works, like we just saw the demo. Theoretically, on paper, it works. Was that program, the victim program, vulnerable? It's really hard to say. Because IBM completely removed it from the operating system after the logic of breach. Was that because of an update? Was that because no one needed it anymore? IBM doesn't talk about vulnerabilities. You can't even get a published list of vulnerabilities on the platform unless you sign away your first child. So we don't know. We don't know if it's vulnerable or not. We just know that the program itself would work if we had a vulnerable program to use it against. Now again, I said this earlier, if you want to learn more about buffer overflows and that sort of attack on the mainframe, so quick aside, we submitted a talk to DEF CON before we knew we could get buffer overflows working. And so Chad put in a lot of work to get that working. He's a genius. Watch that part. Don't watch my half of the talk, just watch his half of the talk if you want to learn more about buffer overflows on the platform. Mainframers for years were saying that buffer overflows don't work, and then he proved them wrong. Right? It definitely works, just no one put the time in to do the research. And a huge thanks, so to the Mainframe Hacker Society, just a big thanks to that community. Again to Chad, who helped with parts of this talk, helping me understand what's going on behind the scenes. The Logica hackers, wherever they may be. IBM for making the platform and not stopping me from giving talks about it. And then if you want to see the slides, they're all available on the archive. If you go to archive.org/details, all you got to do is press the power on button, and it'll turn on the emulator, and you can see all the slides. So with that, any questions? Wait, hold up. That aren't about my computer, that are just about the talk. Any questions? Yes? Has IBM added any stack protection? No. They have something similar to a canary, but not. Just go watch the buffer overflow talk that Chad gave. It explains everything. Any other? Yes? Did I? Of course I respond. Okay, the question was, did I respond to the Twitter DM? I 100% did and said, thanks. This was I figured this out last year, how to get this code working. It's the first time I had to sit down and do it. So I didn't really have the time to go and update them and say, yes, it works. I don't know if it was a vulnerability. It doesn't matter now because the operating system's been updated 6, 7 times since then. So there's no one running a vulnerable version of the OS, I hope, today. It's not like Windows. It's not like Windows where you have like Windows XP just hanging out everywhere. IBM eventually stopped supporting a product, and so you can't call and get help anymore. So if something breaks, it's done. So people upgrade. Yes, question? Yeah. So the question was, do I have a mainframe for doing research like this? Like, how would people in the audience get to participate? So there's two ways you can go about doing this. There's one called Hercules. It's an open source Z architecture emulator. It is verboten at IBM to have a copy of it. But basically, it's a full-on emulator. However, you can only run older versions of ZOS, I'm told, or the open source. It's not open source. It's so old it went public domain operating system. Okay? Yeah. But all the concepts are the same. It doesn't have Unix built in, but it has everything else. So if you wanted to get started with like just playing around, you can install Hercules, literally apt-get install Hercules. And then download turnkey MVS, and you can have a mainframe up and running to muck around with. And then IBM has a product called ZPDT. The name changes all the time, okay, so bear with me. ZPDT, and then they call it sometimes RDZ, and sometimes they call it Rational Developer Unit Test for System Z. One of those search terms will get you what you're looking for, but basically, you buy a license. It's not cheap. It's like, I think $5 grand, $10 grand. Yeah, but how much are you paying? If you're an enterprise, how much are you paying for Qualys? How much are you paying for other security products, right? So you get a full copy of the most up-to-date operating system, and you get an emulator that will run on a laptop, on a server somewhere, and you get a license key on a dongle, and then you can boot up the operating system and run the current state-of-the-art ZOS on a laptop. It's what we use to do research and development. Does that answer the question? Yeah? Okay. Yes, question? Okay, so the question was, would you be able to see this in like logs? So if I'm doing racf commands, so like in the demo where I changed my permissions in racf, that would 100% get caught, right? Like that would create a record in SMF. That's what they call logging, like syslog. That would create a record, and someone could find that and see that. There's a reason why the hacker didn't do that, and there's a reason why the hacker didn't change the special or operations bit, but instead changed the ones that only impacted Unix, because those wouldn't get logged. There are products today that exist that will track you changing your ACE flag in memory today, but I can't tell you how much that happens. I can't tell you if they're getting tons of reports. So, but yeah, you would catch that, but you have to install a third-party product. Anything else? Yes, question? No, because you can just find that on Shodan, or just watch a Vis talk on stuff he's found on the internet, right? Every once in a while, he'll send me something, be like, hey, is this what I think it is? And I'll be like, it looks like AS400. For the record, I do know the location of every single AS400 on the internet. I just don't post screenshots because they all look exactly the same. So I'm not giving that database up, but it's super easy, just mass scan port 992 across the entire internet. And then nmap that, and anything, all of it's going to show up AS400. I have like thousands. Yeah, I mean, whatever. I don't care. Like, if Costco wants to put their AS400 on the internet, who cares? Like, whatever. It's no different than an employee login page to me. Any other questions? All right, good. All right, well, thank you so much for having me. This is awesome, and enjoy the rest of the conference.